Hey, welcome back to Epstem. We hope everybody had a great holiday season and that just things are going well. This is our first episode of the second season of Epstem. We're excited to kick it off with a really interesting episode on magnets.
Oh, yeah. Magnets are kind of all over the place, as you probably know. They're in a lot of things we use every day, including motors, which are pretty much they're in most electronics anyways. They're in servos, which are really important for any kind of control system. A servo is basically just a motor that can control where its location is. So instead of just spinning, it's going to be aware of what position it's in, and you can control that with really any kind of controller, like a joystick or a knob or something like that. So magnets are in those, critical to the function of those as well. Yeah, magnets are kind of the science behind wireless charging, or what's known as inductive charging. Basically, electricity moving through a wire creates a magnetic field, and moving magnetic field, that is, can induce a current in a wire. So that's basically how a wireless charger works. Is you run electricity through a loop, it makes a magnetic field. That magnetic field affects another wire that would be inside of like a phone or whatever it is you're charging, and that magnetic field would cause a current. It would generate a current in your device, which is what charges it. So magnets are all over the place, and they're really cool. So let's go ahead and learn some more about them.
I'm Hunter.
And I'm Luke, and you're listening to Epistem, a show where we explore papers in STEM fields and let you know what they're all about. The name of the paper that we'll be looking at today is Manipulating Magnetic Fields in Inaccessible Regions by Negative Magnetic Permeability. We found this paper on Archive, and it was published in the Journal of Physics by some researchers at Cornell University.
Magnetic field manipulation is used for many common applications. As Luke already explained, it's used for wireless charging, electric motors, alongside of other devices such as micro-robots. All of the aforementioned applications involve using close proximity magnetic manipulation, but these researchers present possibilities for, in words of their abstract, remotely shaping magnetic fields. So this would involve changing a magnetic field from a remote location or just farther away than we are doing currently.
And that's kind of one of the weaknesses of using magnets in control systems, is that they generate a magnetic field, which is useful and use it for a lot of things, but it's not very controllable, and it's not very precise.
Yeah, a way that you can see this in your everyday life is just if you have a wireless charging phone, if you take it off of your, if it's not sitting correctly on your wireless charger, it won't charge correctly and so on, because it needs to be aligned so close and in such a close proximity that that can affect a lot of different means, whether it be in a motor or wireless charging. Magnetic fields can be used for manipulation in places that are remote in the world itself through this technology. So possibly using magnets to manipulate things in the Arctic or in just remote mountain ranges that we don't have access to create an infrastructure for like electrical systems in general. The theory of this paper is based primarily on negative permeability magnetic materials. Just a little background on magnetism itself. Permeability values are given to classify materials as diamagnetic, paramagnetic, or ferromagnetic, each increasing their value threshold more than the last. Thus, diamagnetic materials have low values and are not ones that you would consider having magnetic properties. On the other end of the spectrum, ferromagnetic materials have a high value and would be considered to have a strong magnetic property. A diamagnetic material has a permeability value between 0 and 1, paramagnetic is considered between 1 and 10, and a ferromagnetic material is considered above 10 microunits. A truly negative permeability was at one point thought to be impossible, but these researchers have gathered data to prove that a material can have a very minimal magnetic permeability relating close to negative.
So we're talking about the permeability value. I'm thinking like a magnet. A high number means a strong magnet, right? For its permeability. And I guess what a magnet does is, with its field, it's able to push away or attract another magnet or something that responds to magnetism, like iron, something that's ferrous, right? But I can see where you would make that field weaker and weaker as it gets closer to 0. but it's kind of difficult to imagine what something would be if it was negative permeability. I guess it would take away the magnetism of another field. It would be like a black hole of magnetism, if that makes any sense. It's kind of a difficult thing to visualize.
Yeah, in theory, something that would have negative permeability would essentially take in the magnetic field that's being imposed on it and direct an opposite magnetic field from that.
Okay. So it like cancels it out.
Yeah, pretty much. Although a negative permeability is impossible, these researchers were able to mimic a value of -1 by having two low surface current densities on the inside and outside of a cylinder that they created, so essentially making a wire, as they call it within their research, and as just a better reference for visualizing it. After immense testing on this wire-like substance that they created, they were able to test it under different currents and with different magnetic sources being directed at it, and the researchers were able to confirm that by changing the current in the system and using varying magnetic relations, they could cancel the magnetic source of the wire remotely. They derived an equation to calculate how much current and at what frequency they needed depending on the size and distance away from the system. If you really want to go more in depth into this, you can look at the equation yourself by finding this research paper. It's just hard to explain in a podcast terms, but it's a really cool and interesting equation that they derived. And if you are interested, definitely go and check it out.
Well, before we get too caught up with the equations and all that, let's take a quick break. All right, welcome back. So, what are some of the applications that might come from the outcome of this research?
Yeah, so the researchers believe that their studies can be very useful in a lot of different applications. Currently, magnetic systems are used to control micro-robots for drug delivery within the human body. However, this technology has constraints as to how much these micro-robots can move due to them eventually losing strength of magnetic control. Where this remote magnetic manipulation could be utilized is to be able to control these micro-robots at greater distances and with greater control than before. Because of the studies that were done by these researchers, they did find that they can remotely turn off these magnetic signals. So once a micro-robot is done being used for drug delivery, they can essentially turn it off and allow for the body to process it, as they do now. However, they aren't able to technically turn it off as of now.
And by turn it off, I guess that means removing its magnetic properties or cutting that link of control between whoever's driving this thing and it.
Yeah, exactly. So it makes it so that they don't get affected by magnetic properties, which could essentially affect something later on in the line if they still have those magnetic properties, which is just beneficial to remove those.
Yeah, I've seen little videos of those little mini robots being used to deliver treatments to cells with some precision because you can actually control the little robot thing. It's like a little mini surgeon inside your bloodstream.
Yeah, exactly. And that's the really cool thing. And the good thing about being able to control these more remotely is that people will be able to surgeons or whoever is guiding these micro robots will be able to control them deeper into the body. So as of now, you lose your magnetic signal and aren't able to get through certain depths of the body due to just everything getting in the way and hindering that magnetic signal.
Yeah, so it allows you to get further in, get a little bit deeper.
Mm-hmm. Exactly.
That's pretty cool.
Yeah. Another technology that this magnetic or remote magnetic manipulation can be used for is transcranial magnetic stimulation, or TMS. So this is used to send magnetic impulses on parts of the brain to modulate neural activity. So researchers and scientists are using this to help with, they're researching more into it as of now, but they're looking into using magnetic impulses to help people with depression and other means to activate neural activity within parts of the brain that aren't getting enough neural activity.
Yeah, that's pretty interesting. Yeah, I'm reading how it can be used to improve depression symptoms
Yeah,
for regulate like mood control and things like that.
yeah, and the cool thing about this research that was talked about in this paper is that it would allow for TMS to be better targeted and be able to be focused better than it is currently.
And that'll be increasingly useful as our understanding of the brain increases.
Exactly.
I'd imagine.
I'd hope so, and I'd imagine so also.
Yeah, it's kind of funny because it uses the same fundamental technology as a wireless charger. It's just inducing electrical activity.
Yeah, we are actually being charged.
Yeah, more or less.
A third use that the researchers talked about for their technology would be for atom trapping, which currently uses magnetic fields to trap atoms, but it's hard to concentrate the location of these magnetic fields using current methods.
Yeah, so with magnetic trapping, it's kind of interesting. It's exactly what it sounds like. It's literally using a magnetic field to, you guessed it, trap atoms. Most of the time atoms have, or all the time? I'm not really sure, I guess. Many atoms have a magnetic moment, which is just a field, really, a direction and a magnitude of a magnetic field around the atom. And if you have a magnetic field that lines up with that atom, with that atoms, it'll kind of lock it in there. So it's used a lot in achieving Bose-Einstein condensates, which is just a really super cold atom. Basically, it's about as cold as we can get something. But yeah, this technology is used in trapping those atoms that are very cold.
If you've done any studies into Calculus 3 at whatever university you studied at, if you think about field arrays and the direction of a specific field, researchers and scientists use that field arrays to actually target and figure out where the magnetic field is going. Yeah, so they use those and use, I guess, Calculus 3 knowledge to be able to calculate how they should trap these atoms and I guess what their movements are going to be like. So those are some of the great uses for this technology that the researchers are working on. But they do have some downsides that they want to do more research into, and that is they don't know the actual effects of having a stronger magnetic field between the system that's radiating that magnetism and the system that they're trying to remotely control. So essentially by allowing for remote magnetism or remote magnetic manipulation, they create a larger and stronger magnetic field between the systems that they are unsure if that affects anything that it shouldn't yet. So they're doing more research into that. But besides that, it seems like a very promising technology that could be helpful in the medical and many other fields.
Absolutely. So we thought we're going to go ahead and close the episode out today. Again, if you're interested in learning more about this paper, its title was Manipulating Magnetic Fields in Inaccessible Regions by Negative Magnetic Permeability. The researchers working on this paper were Rosa Mock-Batla, Mark G. Basin, Nuria Del Valle, and Jordy Pratt-Camps. Thanks for listening, and if you enjoy the episode, feel free to follow us on Instagram. It's epi.stem.
If you want to reach out to us on our email, it is epistem.pod@gmail.com. So the paper that we looked at today was actually sent to us by a listener, Connor Polanka, and he sent us a paper because he wanted us to check it out and be able to, digress what was in the paper. So if anyone has a paper that they've seen that they want us to go over, or just something that maybe goes over their head that they think that we can figure out and explain to them, have at it and send those papers our way. We'd really appreciate it.
As usual, if you want to support us, you can do that either through our page on Anchor, which is anchor.fm/epistem, or through Patreon, patreon.com/epistem.
Keep on learning.